Hello grade 11s. In this lesson we're going to look at two things, pH and stoichiometry. This is part one of a two-part lesson. We'll begin with pH and then we'll move on to the stoichiometry of solutions. About the stoichiometry of solutions, you've already practiced stoichiometry quite a bit through mass and mole conversions and using stoichiometry to figure out the moles of one substance in a balanced reaction to the moles of another. So extending this now to solutions is actually not too difficult. You have a good background in this. So that, however, will be part of our part 2 lesson. So a different video, I'll connect it on YouTube as a playlist. So we'll start now with pH. Okay. So pH stands for power of hydrogen. What that really means is it measures in a logarithmic scale the concentration of hydrogen. Okay, making sure my correct pen there. Something I should say about this. So when an acid dissociates, and we'll talk more about acids later, but when an acid dissociates, it produces what we know, what you've heard in the past as hydrogen ions. Hydrogen ions are so reactive that in the presence of water, which they will be in, they will create what's called hydronium, H3O+. And notice this exists in a 1-to-1 ratio. So saying concentration of hydrogen or concentration of hydronium is essentially the same thing. In fact, what mostly exists, what is really happening is actually hydronium, not just hydrogen ions, because they will react. Hydrogen ions as a product of the ionization of an acid will react with water to produce hydronium. So these are almost interchangeable. So if you hear me say hydrogen concentration or hydrogen ion concentration or hydronium concentration, they essentially mean the same thing. Okay. So I mentioned, or I said that the pH of a solution is measured in a logarithmic scale. It's a negative logarithmic scale. We'll look at that and what that means. But essentially, a logarithm means a base 10 to a certain power. Okay, and that will give you a function that looks something like this. You may have seen that function in your math classes, that sort of shape. Okay, cheesy joke. You can move on. Logarithm. Log has rhythm. Get it? Moving on. Okay, these are the formulas we're going to use. So pH is then measured as the log of a concentration of hydrogen ions, and we know that we can replace concentration of hydrogen ions with hydronium. Right? So it's a negative logarithm log of the concentration of your hydrogen ions or hydronium ions. Now you can manipulate this formula and you would get this next one. So if you have the pH value of a solution, you can then do the opposite. You can figure out what the concentration of hydrogen ions is by just putting it to a base 10 as an exponent of the negative pH. It'll make more sense with some examples. All right, so our first example. Here we have a question that says to find the pH of that concentration. We know big M means molarity, which means moles per liter, of H2SO4, and that should actually say aqueous. I'll fix that in a bit. So this acid dissociates in this form. So here it says aqueous, there we go. So in a 1-to-2 ratio and in a 1-to-1 ratio, so 1-to-2 to 1. Okay, so this is not really relevant, but we do need to write that down. What's important here is as we compare this acid, sulfuric acid, with the ion that it produces through its ionization. Okay, it also says that we have concentration that much, 0.007 moles per liter. We can figure out in a 1-to-2 ratio what that means. So 0.007 multiply that by 2 because it's a 1-to-2 ratio gives us this. I'm just going to move this off to the side. Okay, and I believe I have my work here. So in a 1 to 2 ratio, we're going to multiply this by 2, and we get that. So that's a concentration then of your hydrogen ions. This is a concentration of your hydrogen ions. Okay, then we're going to plug that into your pH formula. pH is equal to the negative log, right, of the concentration of your hydrogen ions. Just plug this into your calculator. Now, depending on your model of the calculator, you might need to type log and then 0.014 or just 0.014 log. Play around with it, but you should get an answer of 1.85. Don't forget to put that negative sign, otherwise it will read negative 1.85. Right, so that's 1.85. Next, now we're going to do the opposite. So here we have a pH reading of 10.3. We're going to figure out what the concentration of hydrogen ions is. So here's your formula. Plug that into your exponent. Don't forget the negative sign there. All right, so it's 10 to the exponent of negative 10.33. Plug that into your calculator and you get 4.7 times 10 to the negative 11. This is a very small number. That 10 to the negative 11 means there are 10 zeros to the left of the 4 followed by a decimal. It's a really small number. That should make sense. This pH reading is quite high, and if you remember our pH scale, I believe I had it here, right, going from 1 to 14, you know, it doesn't stop necessarily at 14, nor does it stop at 1 on either end, but this is commonly what you've seen. Anything that is acidic has a lower pH, anything that is basic has a higher pH. So that pH value of 10.3 roughly here, that means it's quite basic. So you don't expect to find much acid inside a basic solution. That's why we have a concentration of hydrogen ions in this basic solution that is quite low. Okay, now you talked about pH, we can, and also the concentration of hydrogen ions. We can then also talk about the power of hydroxide, or POH. In a similar way, it has two formulas just like pH. You can figure out POH by the negative log of the concentration of hydroxide ions. You can also find the concentration of hydroxide ions by doing something similar, 10 to the power of POH if you have pH or the POH value. Now how pH and POH are related is if you add pH and POH, you get 14. So the pH of a solution and the POH of that same solution, you add them together, you will get 14. Okay, so using that, we're going to now solve a problem, right? And this is the last example we're going to do. We're going to finish this first part of our lesson on pH. Here's a question: determine the pOH of a 0.006 molar solution of, and this is an acid, phosphoric acid. Okay, so let's do that. Okay, so let's write the ionization or the dissociation equation of H3PO4. Okay, it's aqueous, meaning it's inside water. It will dissociate to look like this. Okay, the important ratio here is between your acid and your hydrogen ion, which is a 1 to 3. Right, so the question says that we have 0.006 moles per liter concentration, right, of your acid. Because of the 1 to 3 ratio, all we need to do is multiply this by 3. So to go from one to the other, your mole ratio from the last unit stoichiometry is 1 to 3. So all you do is multiply that by 3 and you get 0.018 moles per liter. All right, so don't get too excited here once you see a number because it's the concentration of an acid. Don't plug that into your pH. Again, pH is equal to the negative log of the concentration of hydrogen ions. Don't plug that into your formula because this value here is not the concentration of hydrogen ions, it's a concentration of your acid, and that's two different things. Okay, so all we now do is pH is equal to the negative log of, from this formula here, and from this value that we determined, 0.018 Okay, pH is equal to 1.74. All right, but I don't think the question was asking us to figure that out. It was saying determine the pOH. Right? We have pH. We also now know that pH plus pOH is equal to 14. If we want to figure out what pOH is, we should isolate for that. We get 14 minus pH. That is 14 minus 1.74. And we get 12.25. So that should be 12.26. Change that. At any rate, this is your pOH. Okay, a little bit counterintuitive. It's hard to visualize this. So pH scales go in opposite directions. So pH is typically 0 in this case to 14, where these are acidic pH values. A pOH scale is the opposite. So the larger the number, the more acidic it is. The lesser the number, the lower the number, the more basic it is. Right. So it makes sense that this acid has a 1.74 pH value, meaning it's quite acidic. So it's going to then have a higher pOH value, in this case 12.26. And you're done. Hopefully this helped. There is a pH worksheet for you posted online already, and we'll continue in our next part 2 of the video with stoichiometry solutions.